Today we are going to be studying two different light phenomena, the interference and the diffraction of light. So we have seen before that in order to study the interference of light, we must have a double slit board. So over here on that board, as we can see, we have multiple slit width. So A, it corresponds to the slit width accompanied by a certain separation. For the first slit width, we have a width of 0.04 millimeter and a separation between the slits of 0.25 millimeters. For the second one, we also have a slit width of 0.04 millimeter and a separation between the two slits of 0.5 centimeters, while for the third one, we have a slit width of 0.08 millimeter and a separation of 0.25, and for the final one, we have a slit width of 0.08 millimeter and a separation between them of 0.5 millimeters. That would be for the double slit. Then over here we have the single slit board or apparatus, which consists of 4 different slits of different width. So the first one would be of 0.02 millimeter, the second one of 0.04, the third one of 0.08, and the fourth one of 0.16 millimeters. So let's begin with a diffraction pattern. So for the diffraction pattern, we are going to be using the single slit. Over here we have the light source. The light source is going to be illuminating that slit, but more specifically for the first part, we want for the light source to be illuminating a certain slit width of 0.04 millimeter. So for the first part, you are going to rotate that board, that diffraction board, until light is illuminating the slit width of 0.04 millimeters, and then you are going to approach that width from the light source. You are going to approach the slit from the light source. If you look at the other end, we have a screen over here, and the screen is located at around 1 meter from the light source. So over here we can clearly see that we have a certain diffraction pattern which consists of a central bright fringe. So over here we have a central bright fringe, then followed by a minima which is basically a point where you have destructive interference. So over here in the middle we have a constructive interference between the light waves, followed by a minima where you have a destructive interference, followed by another bright fringe, followed by a minima, by another bright fringe, so on and so forth. And in a similar manner, over here we also have a certain minima, followed by another bright fringe, followed by a dark fringe, so on and so forth. So the target in that part would be to determine the distance from the center of that central bright fringe to the first minima, to m equal to 1, then the distance from that center to m equal to 2, then to m equal to 3, etc. So for that matter, we are going to bring the following paper. And first off, you need to mark or you need to trace the borders of that central fringe. So over here we are going to place a certain mark in that place, which is an indication of the border of that fringe, and another mark on the other side, which is an indication of the other border of that central fringe. So in that case, you would be able to easily locate the center of that fringe. And over here, each border would correspond to m equal to 1 on each side, on the right side and on the left side. Then in a similar manner, you are going to indicate the border of the first bright fringe on the right side. Then you indicate the border of the third minima, which is the border of the second or the third bright fringe on the right side. Then you are going to remove the paper. Using a ruler, you are going to locate the center of that central bright fringe. So over here in the middle, we have the central bright fringe width. Then what you are going to do in that case, you are going to be measuring the distance from that center of the central bright fringe to m equal to 1. So that point over here corresponds to m equal to 1, which is the first minima. So you measure the distance y, then you measure the distance from the center to m equal to 2, and that would be y2, which corresponds over here to the second minima, and then you have to do the same thing for m equal to 3, where you have the third minima. So after determining these values for y, which are the distances from the center to each minima, then you are going to be determining in that case the value for the wavelength of that laser light. So you are going to be applying the equation which we have derived before. You already have the order, which is m equal to 1 for the first minima, m equal to 2 for the second minima, and m equal to 3 for the third minima. So having the orders, having the separation between the laser light or between the slit and screen, having the separation between the slit and screen, that would be D. And having over here the slit width W, therefore you would be able to determine the wavelength of the laser light. That would be for the first part of the experiment, which has to do with the diffraction. Now moving on to the second part of the experiment, where we are going to be studying the interference pattern. So as we have seen for the interference pattern, we must have a double slit interference and a certain separation between the slits. So for the first part, if you look at that table, you have to start with a certain slit width of 0.04 millimeter and a separation between the slit width of 0.25 millimeters. So over here, you are going to rotate that board in order to have light shining through or eliminating the slit width of 0.04 and the separation between them of 0.25 millimeters, and you approach it from the laser light source. So if you look at the other end of that track where we have the viewing screen, we can clearly see now that we have an interference pattern which is kind of similar to the previous diffraction pattern. However, that interference pattern now it has a special feature, so that central bright fringe is now being divided into multiple small bright fringes, which we have referred to as peaks. So the interference, it has a special criteria, which is that each central fringe or each bright fringe is going to be divided into several small bright fringes. So in that case, as we have seen before, what we need to do is we need to measure the width of each bright fringe. Then you are going to be counting how many small fringes you have within each fringe in order to determine the separation between two consecutive dark fringes or two consecutive bright fringes. So for that matter, you are going to bring that paper, you are going to mark the edges or the border of that central fringe. So after marking the border, now you are going to be taking a certain picture of that central fringe. You are going to enlarge it in a clear enough manner in order to count how many bright fringes you have within that central fringe. So after counting the number of maximas in that case, and after having determined a certain value for the width of that central fringe, what you are going to do in that case, you are going to be determining y, which is going to be w divided by the number of maximas. And therefore you would determine a certain value for y over here. Then in a similar manner, you are going now to repeat the same thing all over again for that bright fringe on the right side. So you are going to mark its border. You have to count how many bright fringes you have within that bright fringe, within that entire bright fringe, which is located on the right side. Then, after determining the width, let's say W prime of that bright fringe, and after counting how many number of maximas you have within that fringe, therefore Y prime would be W prime over the number of maxima. Now in that case, after determining several values for the separation between two consecutive dark fringes or two consecutive bright fringes, now you have to determine the wavelength of that laser light. So to determine the wavelength, you already have the separation Y, you already have the order, which, like I've said before, it's going to be 1 for all fringes, since we are studying each fringe as a sole entity and not with respect to the central fringe. And then you have the separation between the slit and screen, and you have the separation D between the slits. Therefore, you would be able to determine, in that case, the wavelength of that laser light. So it appeared that in the previous part, the interference pattern, it wasn't viewed clearly enough in order for you to notice how each bright fringe is actually being divided into several small maximas. So if we have a look at the central bright fringe, we can clearly see that that central fringe is being divided into small bright fringes, which we label it as small peaks or maximas. So what we did in that case, we counted how many bright fringe or how many small peak we have within that central fringe, and after measuring the width, we divided the width by the number of maximas for that central fringe in order to determine the separation between them. And the same thing for the first bright fringe on the right side, and the second bright fringe on the right side, and the third one. So we have basically, we have been counting the number of maximas for each fringe, we have been determining the width, and then we have divided both values in order to determine the separation between the peaks, between the maximum peaks.